We're going to look at a strong acid being titrated by a strong base, and then a weak acid being titrated by a strong base. And what we're going to focus on is what is in solution at every point during these curves, what reaction is occurring at every point, and then how should you be thinking about the pH. Starting with the strong acid being titrated by a strong base, at the very beginning of that curve, we only have the acid in solution. So for this particular one, there is only HCl in solution. And anytime you have a strong acid in solution, it's going to react with water, and it's going to completely react to create H3O plus ions in whatever anion it was attached to, which in this case is Cl minus. For the strong acid, all of it completely reacts. So at the very beginning, we had 50 milliliters of 1 molar concentration of HCl, and that's 5 times 10 to the negative 3 moles of HCl. All of that reacts, so we lose 5 times 10 to the negative 3 moles of HCl, and we produce 5 times 10 to the negative 3 moles of H3O plus. We don't worry about the H2O because we never worry about H2O concentrations whenever we're dealing with reactions, and we also don't worry about the Cl minus because it's not going to be reacting with anything else. What we would do from here is do negative log of the H3O concentration to get the pH. So the 5 times 10 to the negative 3 needs to be divided by the volume and then plugged into this equation. Now as you move along the x-axis, we're adding sodium hydroxide, which is causing that pH to increase. And we're going to be asking ourselves what's happening in solution during the red part of that curve. When the sodium hydroxide is added, it's going to completely dissociate into sodium ions and hydroxide ions. The hydroxide ions are a very strong base, and they're going to react with any acid that's in solution. Since the HCl completely reacted, we have none of that left, so the only thing left for the hydroxide ions to react with are those H3O plus ions. Now let's write a reaction to show that happening. The H3O reacts with the hydroxide ions, and that creates 2 molecules of water, because one of the hydrogens from the hydroxide ion moves to the OH minus ion. Now that we know what reaction is happening, we need to think about how do we calculate the pH during that red portion. The first thing you need to be able to do is to calculate the number of moles of OH minus. That can be calculated by taking the volume of the NaOH that's added and multiplying it by the molarity of that solution. And in this particular problem, that molarity is 0.1. You'll find the volume by using the x-axis at whichever point on the curve you're working with. Once you find that number of moles, and we'll just say that's X, you know that it's going to completely react with H3O plus ions because it's such a strong base. That means that the amount of H3O plus that we started with, which we calculated before as 5 times 10 to the negative 3, is also going to lose X amount of moles. That leaves us with no more OH minus because all of it disappeared, and then the final H3O plus concentration is just whatever you started with minus the number of moles of OH minus. And then once again, just plug that right in to negative log of the H3O plus concentration. Again, this is what you do for any point at that red highlighted portion of the curve. Once we hit the midpoint of the steep slope, we have reached what's called the equivalence point. At the equivalence point, the exact same reaction is happening that we already have written, but there's something special happening with the amount of OH minus that we added. However many moles of OH minus that were added, which you can calculate this exact same way, will be equal to the number of moles of acid that were in solution. For this particular problem, we know that the moles of acid was 5 times 10 to the negative 3. Since we have the same number of moles of H3O plus and OH minus, they're going to completely react with each other until there is nothing left. Since there is no H3O and no OH minus, that's what explains the equivalence point of a strong acid, strong base titration being perfectly at 7, because all of those have just turned into water. Now let's look at what happens after the equivalence point. We have a new reaction happening because there's no H3O plus for the OH minus to react with anymore. As we continue to add sodium hydroxide, the sodium hydroxide is completely dissociating and the OH minus has nothing else to react with, which means we just need to find the moles of OH minus added and divide that by the volume of the solution. That's going to give you the concentration of the OH minus, which you can then plug into the negative log of OH minus to find the POH. The pH can then be found by doing 14 minus the POH. When you're finding the number of moles of OH added, you're using the same equation that we've been talking about, but the volume that you're using is only the volume that's been added after the equivalence point, because all of the OH added up until the equivalence point has been completely reacted. Now let's look at what happens when a weak acid is titrated with a strong base. Starting at the very beginning, we only have the weak acid in solution. The weak acid, which is hydrofluoric acid, reacts with water to form H3O plus and F minus ions. Since this is a weak acid, it barely reacts, and you have to do an ice table to figure out how much H3O plus is created. I'm not going to go through how to do an ice table in this video, but you would use it to get the concentration of H3O plus and then plug that in to negative log of the concentration of H3O plus. Keep in mind that the H3O plus concentration is not that high because FH is a weak acid, and that explains why the pH is not that low compared to where it is for a strong acid titration. After this, we start adding some base, and we'll talk about what happens during that red highlighted portion. What happens now is quite a bit different than what happens during the strong acid titration, because FH does not completely dissociate like HCl does. In fact, most of the FH is still unreacted. So when we add NaOH, the OH minus is going to be reacting with that unreacted FH, and that's going to produce H2O and F minus. Since most of the FH is unreacted because it's a weak acid, we still have roughly 5 times 10 to the negative 3 moles of FH remaining. Once we start adding NaOH, we can calculate the number of moles of OH minus using that same method as before. Let's say that we added X amount of moles. The OH minus added will completely react with FH, so we end up with 5 times 10 to the negative 3 minus X for the number of moles of FH. And for every molecule of FH that reacts, we produce a molecule of F minus, so we produce plus X moles of F minus. As we move to the right on the x-axis and add more OH minus, we're losing FH and creating more F minus. This means that X is a significant number, and we are creating a significant amount of F minus. And as long as we're not completely reacting with all of the FH, we still have a significant amount of FH left. And this means we have significant amounts of a weak acid and its conjugate base. And anytime you have both of those in solution, you need to be thinking about the Henderson-Hasselbalch equation. The pH is equal to the pKa of the acid, and for FH, the pKa is 3.2, plus the log of A minus over HA. So once you figure out your HA and your A minus, you just plug them into the Henderson-Hasselbalch to get your pH at that point of the titration. This is especially helpful to understand the half equivalence point, which I've drawn a yellow dot to represent that. At the half equivalence point, we have added just enough OH minus to react with half of the FH. For this one, that would be 2.5 times 10 to the negative 3 moles of OH minus. That means we'll lose 2.5 times 10 to the negative 3 moles of FH. We'll lose all of the OH minus because that completely reacts, and we will produce 2.5 times 10 to the negative 3 moles of F minus. We'll be left with 2.5 times 10 to the negative 3 moles of FH, 0 moles of OH, and 2.5 times 10 to the negative 3 moles of F minus. When you plug these numbers in to the Henderson-Hasselbalch equation, you end up with log of 1, and log of 1 is equal to 0. So then your pH is equal to whatever the pKa is for that acid. This is a super important fact that will help you with a lot of titrations to remember that at the half equivalence point, pH equals pKa. Now let's look at what happens at the equivalence point. The same reaction is happening where the OH is reacting with the FH. Only this time we have added the same amount of OH minus that we had of FH. That will completely react with all of the FH and we'll be left with 0 FH and 0 OH minus, and we created 5 times 10 to the negative 3 moles of F minus. Since we now only have F minus in solution, that's the only thing that's going to be reacting, which means we need to write a reaction to show F minus reacting with water. F minus is a weak base and it reacts with water to form OH minus ions and FH. What we have here is just a weak base problem. So you would do an ice table to find the OH minus concentration, which then you could plug into negative log of OH minus to find the pOH, and then do 14 minus the pOH to find the pH. After this point, when we keep adding more sodium hydroxide, just like with the strong acid titration, there's nothing left for it to react with, so it's going to dissociate and directly increase the OH minus concentration. You'll need to find the moles of OH minus added, which we've already discussed how to do. Once again, make sure you're only using the volume added after the equivalence point in that calculation. You don't have to consider the OH minus that's still in solution from that F minus reaction because it's negligible compared to what we're adding from sodium hydroxide.